Well, hello, everyone. This is Bob Sullivan with Pureline. I'm the president of Pureline, and I am joined today by one of my very, very long-term good friends, Greg Bova. Greg Bova is the director of engineering at Johns Hopkins Medicine. Originally, I said Johns Hopkins Hospital, but that only includes the hospital, and Greg is over much more than just the hospitals. So, Greg is he's the engineering director for Johns Hopkins Medicine. I have known him for 15 years, and we have done a lot of business with them in terms of chlorine dioxide and Legionella control, et cetera. And I'm proud to say that Greg has put together a great document. I actually have a copy of the document, but a little booklet that really describes the Johns Hopkins program and the successes that they've had for the last 23 years. So with that, Greg, you want to go ahead and take it from here?
Sure. Welcome, everybody. I hope you had an opportunity to read the paper. If not, please do. We're going to the 24th year, and but this paper depicts the 23 years, but we're still negative, and but I think you might enjoy what I present. And we're presenting primarily the water treatment side of things, but there were some other facilities related items that we did correction to improve the efficacy of the chlorine dioxide. So here I'm going to jump into the slideshow, and at the end we'll have a Q&A. All right. So beginning in 2001, we started installing a chlorine dioxide system in 4 of our patient buildings. We actually started looking at water disinfection going 1999, and so I've been here since '86. So it was in our cancer building actually where we started this water treatment. So the data we collected was over 23 years using chlorine dioxide to control and eliminate Legionella. And that's important to recognize that a lot of people want to control, but we started controlling and ended up eliminating. And so the paper details on how to properly apply the chlorine dioxide treatment and the results of a Legionella culturing, the equipment and system modifications that were made to prevent the growth of the Legionella. So the hospital here in Baltimore, we received water from the local municipality, and that's the Baltimore Department of Public Works. And we have 2 feeds around the hospital. One's 100 PSI line, the other's a 40. And so we actually tap into the high pressure line as the primary water source to the hospital, and the backup is the 40 PSI. And we have booster pumps that be activated if we need to. And so we have 2 main feeds coming into the hospital. We have a main loop system that goes all around the hospital and in the tunnel system. And actually, in the paper, I call out that we replaced that main back in 2019. Primarily, it was a galvanized main, and we went stainless steel throughout. And you'll see the results in the graphs and charts I present in this paper. And so the potable water to each building is the cold water feed, and each building has a hot water tap off, and it's pretty much all copper piping. And so we have inpatients buildings A, B, C, and currently we're using a Halox unit, which is no longer available, and we're in the process of replacing these units with the Pureline units. And the reason for that is that we have in building D Pureline units that we've been running now, I close to 15 years with minimal problems, and they seem to be less problematic than the Halox units, but the Halox units, you can't get parts anymore. So we're going to go full Pure Line units within the next 2 months. So the generators were installed at the cold water main to each portable water distribution systems per building. And from there, it was branch piping to the hot water system. But before, and during the treatment of the buildings, we found numerous problems. And, here I highlighted some of the problems that we found. And one is the sizing of cold water piping. And we found that in a lot of the mains were oversized. And so where we could, we put the proper size piping in, and that minimized low velocities in water systems. Also, we found that the hot water supply and return piping were incorrectly sized. And so we had to resize the mains in a lot of these, as well as install hot water return pumps to get good circulation and temperature throughout the hot water system. The hot water return flow was very low, and that's where the booster pumps and return pumps came in, because we have minimal flow on a return. And so what ended up happening is that you have low flow stagnating water conditions, which is really a perfect growth environment for bacteria. Converted diverter valve sizing, thermostat elements. We found that you may have a 2-inch return line and a 2-inch bypass to converters, but only a 3/4 inch going to the converters. So when the diverter valves went to full return back to the converters, they couldn't handle the flow. So we made a full size from the return to the bypass and converters to the converters. And also we found that thermostatic elements were incorrect. I mean, we were trying to maintain a 110-degree return water, but these thermostatic elements were 110 degrees, but they start opening up at 100. And so you had a fluctuation of temperatures on a supply main, and that was critical for us to maintain adequate hot water temperature, not too cold a temperature that was the perfect environment for bacteria growth. We found booster pumps were incorrectly sized or oversized, so we went resized those and also made adjustments to those pumps to eliminate water hammering and things like that in water systems. The other aspect was a manual faucets in place of automatic faucets. So Hopkins did a study, 15, 16 years ago, when we were looking at putting manual faucets, automatic faucets in a building, and we did studies and found out that they grew a lot more bacteria. And I'll show you a little bit more in this presentation. And then we eliminated aerators and went to laminar flow control devices. And aeration is one of the sources of ingesting Legionella, all the bacteria into the lungs. And then the water filtration units. And, we did this because we had issues with city water mains breaking and all kinds of sediment and debris coming in. So here's one of our water filtration systems. What you have is you have the water coming into the unit. These are our filter units. They're basically a basket strainer. It goes down to 20 microns. And this is really to pull the rocks out of the water system. And we found this to be very effective in controlling the sediment and debris coming into the buildings. This is a picture of our hot water heaters and return pumps. You can see the numerous hot water heaters. And we originally only had one hot water return pump. It was 2 towers, and one pump was to do both towers. And we changed out a pump dedicated per tower. And this really improved the operation of the hot water system. We had a fluctuation of 15 degrees. By the time we did modifications to the converters and the return pumps and diverter valves, we had a plus or minus 1 degree variance in temperature. I mentioned earlier, this is a diverter valve. The hot water return comes in, goes to the converters or bypasses. And this line right here used to be a 3/4 inch line. We now make it full size, and because When the converter valves are full return back to the converters, you're not going to pull the GPM through a 2-inch line through a 3/4 inch line. And this is a thermostatic element, and that, they were 110 degrees. Well, you got 107 degrees here, and it starts opening up at 100 degrees. The hot water return is going to bypass the converters, and you're going to get that fluctuation in hot water temperature. So this stabilizes our hot water return and our supply by changing these elements. I mentioned earlier about faucets. Here you have electronic faucets, which have no clinical data that we were able to find saying it causes less infectious diseases. And the reason being is because these faucets have numerous components. They have inline filters, check valves, a solenoid valve, aerators, and we cultured every little section in between, sent it to a third-party lab, as compared to a manual faucet, which only has basically a cartridge that the water comes in, goes through the cartridge, and it goes to the faucet. And when we compared it to, we had about 4 times, 5 times the amount of growth happening in electronic faucets. And these faucets also had a maintenance feature that if they weren't used, they automatically flushed. Well, these faucets were used so often, they never went into operation. The outcome was that all the patient room and all the patient access sinks in the building were changed to a manual faucet. And so electronic faucets are only utilized in public bathrooms. And, and no manufacturer yet has shown us data that's equivalent to a manual faucet related to bacterial growth. One of the key elements we found during our years of operation was that we implemented a daily flushing of showers and sinks, and this occurs when the bathrooms are being cleaned. And our environmental service people are in there cleaning anyway, so why not flush the faucets? And by doing this, we eliminated 2 to 3% positivity in our water cultures years ago, and now it's mandatory that all patient bathrooms and showers and sinks are flushed when they're cleaned. Well, here's one of the Purine generators we installed. It's a nice unit. I mean, I really can't say much negative things about it, if anything. And we're putting these units throughout the whole hospital now. And here's the monitoring. We have a chlorine sensor, 2 cold water deciliters, and then 1 hot water with a hot water sample cooler. And the reason why we had to do that, the hot water was too hot and it interfered with the membrane accuracy. And so we cooled the water down without diluting the water. And the reason why we have 2 chlorine dioxide meters versus 1 on a hot is that the cold water is considered potable. And so if one of the meters starts to fluctuate and you only have 1 meter, you don't know you have a problem until you're doing your daily test. So 1 meter controls, the other one monitors against the other meter. If there's a big differential between 2, it's just down distribution pumps and alarm goes and sets out. Hot water is, people are not drinking hot water, so we only have 1 meter and it's a non-issue. We measure the chlorine level coming in because if the city chlorine level, which Baltimore City uses, is very low, our distribution pumps to the hot and cold water systems will ramp up, and if need be, can be restroked to maintain residual amounts. And we tried different methods of control, and we found direct chemical control to be the most effective. We're running around a 0.3, 0.4, maybe sometimes a 0.5, depending on the conditions. And it maintains the pumps sound like a regular IV drip going into a patient. It's very smooth operation. This is a really great picture, and it's not in the book, but it was part of a 2004 publication, And what this is a 8-inch basket strainer of a incoming water supply to a building. And what you have is Legionella, which I pointed to, and bacteria. And, they will come back negative typically on culturing, but we swabbed it after we saw it, and it came back high levels of colony forming units of bacteria in Legionella. So this is something to be aware of, that you got to make sure your baskets strainers are cleaned. Now here's a good a sample of biofilm Legionella. We had a building and we cut a section of pipe out to put an injection quill, and as you can see here is biofilm, and we cultured, sent to a lab, and it came back Legionella and bacteria. And so we put on our chlorine dioxide system. 3 weeks later, we cut a section of pipe out, just about a foot down from this section of pipe, and this is the condition. We stripped the biofilm out of the piping, and thus we eliminated the bacterial and Legionella growth. To me, it's a very, very strong image of the effectiveness of chlorine dioxide. The only downside in 23 years is that we tested pipe after pipe and heating converter bottom tubes, when they had leaks. At no time, and we sent it to a third-party lab because we wanted to make sure we got the right information. We did not tell them what caused the problems. We identified the top of the pipe, if there was a leak on top of the pipe, side, bottom, and we said, "Hey, we got a leak. Tell us what's going on." And what they found out over the years was we had high velocities and low velocities. There was chlorine damage that caused pinhole leaks, overfluxing. But at no time was chlorine dioxide identified as a culprit. But what we're here at the hospital looked at and mentioned in the paper is that the removal of the biofilm from the inside of piping exposes the copper pipe to chlorine. So you can see accelerated chlorine corrosion rates. But the whole thing is that we looked at other systems to reline the piping, and there was no data on relining pipings when using chlorine dioxide to prevent corrosion, accelerated corrosion rates. And so, we got pricing to install silica systems, and it was just too costly. It was cheaper just to replace the pipes as they had pinhole leaks. So that's the only downside we found in 23 years. And to the hospital, it was a no-brainer. Replace the pinhole leaks as they occur. And one of the other parts about just do it is just that if your hospital or building gets Legionella in it, the locality costs to investigate can easily outweigh the cost of a treatment system and to monitor it. So, keep that in mind as you're looking at treating the buildings. We sample extensively. It's not required to do it, but we sampled the cold water pre and post chlorine dioxide treatment. We sampled the hot water supply, return main. We sampled at the end of each floor, hot and cold water showers and sinks, and we select periodically ice water and dispensers. But one of the critical aspects is that we have a zero detectable limit for Legionella. I mean, a lot of practices is 30%, but we don't care. We want zero. And so we've been running zero for over 23 years. Well, chlorine dioxide operation, we monitor chlorine and chlorine dioxide. We have chlorine dioxide chemical control. We had an effective level max of 0.5 ppm. The max limit by the EPA is 0.8. And we run it 24/7, and we treat both the hot and cold water. We started out treating the cold water, and we found out we needed to treat the hot, and mainly because we weren't getting enough hot cold water makeup to the hot water system. It was quickly being diluted. dropping the levels of ppm of chlorine dioxide. There's been a lot of people talking about, oh, geez, the converters are cooking it off. No, it has nothing to do with that. It's the amount of makeup water mixing with the volume of water in the hot water system that caused the reduction in ppm. So we found that out and corrected that, and now we're maintaining this max of 0.5 ppm in both the hot and cold. Okay, so here's the fun part. So here is building A. This is the oldest building we've been treating, one we've been treating now for almost 24 years. And this chart depicts 23 years of treatment. And so we've done over 3,193 water samples. The red line that's dotted is the Legionella cultures, and the blue is the number of cultures that we tested. And you can see, we had 18%, 20%, but at no time we hit 30%. So it's always been low, but it was not satisfactory to the hospital. We wanted zero. So before we started up, we saw, 18.9%, but it jumped a little bit. And the reason why it jumped a little bit is that we killed off the competing bacteria and Legionella had a chance to grow. So it took a little while and it came right back down. And so, but we were only treating the cold water system at the time. And then we went for almost 11 years, treating just the cold. And then we found out, wow, we need to treat the hot. And once we treated the hot, you can see we dropped off to like 0%. Now we had a little bump and back in 2016 to 18, and we've determined that it was the cold water supply main. We switched over to mains and boom, we've been zero ever since. So this is a very good long-term effectiveness of chlorine dioxide, but it was a lot of things we learned along the way, and we finally got things where they needed to be. So here is building B. Now, building B has been treated for 22 years, and we did over 2,217 cultures. And you can see that the culturing, once again, never went above, 22%, except before we started, we had 47%. So right out the gate, we saw basically a 50% reduction in Legionella cultures by treating the water system. And so you can see that, we bounced, always had some positive cultures. We started treating the hot water system in 2011. We went from 6.7 to 0.9%. And, and we're talking about one culture. I mean, one out of many, 110. And that's back in 2011, we started treating hot and cold water. And so in between 2012 and 2014, we shut the building down. We did major renovations, replaced mains. We had a little startup hiccup, which is only 3 cultures. Yeah, keep that in mind. And we've been negative ever since. And we had a lot to say about what we learned over the first 12 years, and we've been negative ever since. It's a great story. Building C, it's been operational for about 20 years. And once again, we saw some positives of no more than 27%. And in 2011, we started treating the cold water, hot water main, and we saw that low level reduction from like 33 cultures positives to 7% max. So it really made a difference. We shut that building down in 2015 to 2018 for renovations, and boom, it's been negative since really 2018. So that's 7 years of negatives. But once again, keep in mind, I mean, when you're at 4.8%, 8.4%, most people won't even react to that and they'll just monitor. So we found that to be very effective. And Building D, now Building D was one of our brand new buildings, constructed in 2012 or put into operation 2012. And the max we saw was a 0.3 positive rating. I mean, we did a tremendous amount of culture in that building, over 5,000 water cultures. It's a tremendously large two-tower building, and we've been negative ever since. And we applied everything we learned in all the other buildings to this new building. That we did a flush remediation upon startup, and of both the hot and cold, and then we cultured, and we're talking about one positive culture. And by the way, these cultures that were positive were NISA, and which is not really commonly associated with disease. So you look at one positive and 367 non-detected, phenomenal data. So in summary, the proper equipment and design is important. It took us years to learn, but we learned and found it to be very effective. Chlorine dioxide was selected primarily that it was very reactive. You can look at chlorine monochloramines as a treatment, but they have a long contact time to be effective. Chlorine dioxide is a very effective, very quick acting disinfectant that, the water comes in the building within 15 minutes. You could be using that water. You don't have an hour for that water to sit to be effective. So that's one of the prime reasons why we selected it. Daily flushing was very important to eliminate a couple percent positivity in water cultures. How you culture your water was very important. We've exceeded all the recommended and current practices out there, and even today we've do more testing than most labs. Our limits are zero, and it's always been zero. And so it's important to understand that we had a very strict control of our water systems, and then we maintain that and will not change from that. There's a chlorine dioxide startup remediation. We used to remediate with chlorine dioxide, but we haven't done that in 15 years. But when we were doing it, it got to the point where, we're going to do a remediation. Okay, we're going to do a remediation, and then we'll lift the water restrictions and wait for the cultures, because we knew that the cultures would come back negative. And originally, chlorine dioxide was to be used for controlling Legionella. The side effect was we eliminated it, and we continue to eliminate it, and will do so in the future. So, that's it in a summary. But please read the paper. I think there's good information in there, as well as a 2004 paper through the International Water Conference. That's the first time we published, and this is the second time we published. So it's a lot of data in these two papers, but this current paper has the information that one needs to move forward. Thank you.
Thanks, Greg. Greg, as always, this is it's been fantastic. I love the charts because you're really breaking it down into some very good detail. At this time, let's open it up for Q&A.
That's great. If you are in the webinar and have a question for Greg or about chlorine dioxide in general, you can go find the Q&A feature on your Zoom webinar bar. It could be in your browser. If you have the Zoom app, it's kind of within the bar itself. You can submit these at this time. In addition, we will be sending out a follow-up email tomorrow with both Bob and Greg's contact information if you have any follow-up questions for them, along with a link to this recording if there are other individuals that you think that might find this to be interesting. First question coming in is, what testing is required for byproducts like chlorates and chlorates?
Yeah, well, the hospital runs under the control of the Maryland Department of Environment, and they're basically the strong arms enforcer of the EPA. Now, the EPA says you got to monitor chlorine levels, chlorine dioxide levels, and chloride. And you got to do it daily for the chlorine dioxide and chloride. So we test daily, and they will not accept our chemical monitors. We physically have to use the EPA methods for testing. And then once a month, we submit a chemical residual report to MDE. And every quarter, we do a residual summary. And then also the HAA5s and THMs. It's a requirement because they want to know whether or not we will grow HA5s and THMs in the water system, which we do. So that's the requirements.
And guys, you will see this vary a little bit by state. I have different states with different regulations, but Greg gave you a great overview of what many states do.
That's great. Well, at this time, Bob, I think that was the only question that came in, unless anybody has any last minute things they'd like to submit. Bob, is there anything else that you'd like to share prior to concluding today's session?
I do. So we'll be sending out, as Alex identified for you, our contact information. You can contact Greg or myself. If you can see, I don't know if you can see what I'm holding here. Everything that Greg talked about, all the charts and everything, is in a little booklet that he had put together here. And I think it's worth, if you guys are interested, just drop us a note. I'll be happy to send it off to you, or Greg can send it, however it gets there. But it is available to you. And with that, I think that's it.
That's wonderful. Well, thank you all so much for attending today. Greg, thank you for the presentation. We hope that you all found it to be informative and helpful, and we hope you have a great rest of your afternoon. Thank you all.
Thank you, guys. Appreciate it.
Thank you.
Bye-bye, guys.